ठीक है, शुरू करूँ? तो गुड मॉर्निंग एवरीवन। माई सेल्फ। अभी आप लोग सब अनम्यूट हो जाइए और जब भी मैं आपसे बात करूंगा, इंटरेक्ट करूंगा, तब आपने शुरू करना है। ओके, तो अनम्यूट, म्यूट योर सेल्फ। तो माई सेल्फ डॉक्टर संजय गौड़ी, head and assistant professor in Department of Physics, Dr. Ambedkar College, Chandrapur. I am serving here since 1993. So I will teach you the first paper of the physics. The name of the first paper is thermal physics. And in this paper there are 4 units. So first unit is on the kinetic theory of gases. This second unit is on the concept of thermodynamics and the first law of thermodynamics. Then third unit is on the second law of thermodynamics and third law of thermodynamics. And fourth unit is on the thermodynamic functions. So this is the entire syllabus of the first paper, and name of that paper is the thermal physics. So first of all, what is the thermal physics? What is the thermal physics? So thermal physics is the combined study of the thermodynamics and thermodynamics, kinetic theory of gases, and the statistical physics. So here first unit is of the kinetic theory of gases. So today I am going to present myself on the topic kinetic theory of gases. So my presentation includes introduction of this kinetic theory of gases, what is meant by the ideal or perfect gas, what are the various properties of the ideal gas, what are the assumptions of the kinetic theory of gases, expression for pressure exerted by the molecule of the gas, and lastly I will explain the kinetic interpretation of temperature. So first we will see the introduction of this kinetic theory of gases. So kinetic theory of gases is also known as the kinetic molecular theory. According to this theory, the gases are made up of tiny particles, and these tiny particles are called the molecules, and all these tiny particles are in random and straight line motion. They move in all possible directions with all possible velocities. So their velocities of the molecule may vary from 0 to the infinity. Actually none of the molecule is in the having the velocity 0, because all molecules are in motion, so they will have a certain velocity. Then what are the postulate of the kinetic theory of gases? So first postulate of the kinetic theory of gas is that heat is a form of energy. Then second postulate is each substance is in molecular nature. Means whatever be the substance is there, the substance is made up of large number of tiny particles, and these large number of tiny particles are called the molecules of the substance. This kinetic theory of gases successfully explain the properties of the gases. So then we will see the what is the ideal gas or perfect gas. The gas which perfectly obeys gas laws such as hello. Hello.
Hello, sir.
Some students are waiting in the lobby. सभी ज्वाइन हो गए ना?
हाँ, sir.
So now what is the ideal or perfect gas? You have studied this ideal or perfect gas in the 12th standard. So what is the ideal gas? The gas which perfectly obeys gas laws is the ideal gas or perfect gas. So what are the gas laws? You have studied in the 12th Boyle's law, gas law, and there are some pressure laws. When the gas obeys this Boyle's law, gas law, pressure laws at all temperatures and pressure, then such gas is known as the ideal gas. So the ideal gas equation is PV is equal to nRT. This ideal gas equation you have also studied in the 12th. What is the PV is equal to nRT? So where P is the pressure, V is the volume, and T is the temperature of the gas, and N, small n, is the number of moles. Number of moles means in a 1 mole of a gas there are 6 into 10 raised to the power 23 molecules in the molecules are there in the 1 mole of a gas, and here R is the universal gas constant. So in actual practice no gas is the ideal gas. However, we will consider the some gases such as oxygen, nitrogen, helium and hydrogen. These gases are the ideal gases at ordinary temperature and pressure. So these gases will obey the gas laws only at the ordinary temperature, only at the room temperature. When the temperature is low and when the temperature is high, then in that situation these gases will not obey the gas laws, and therefore only at the ordinary temperatures these gases oxygen, nitrogen, helium and hydrogen, these gases obey the gas laws, and therefore we will call these gases as a ideal gas. Then we will see what are the various properties of the ideal gas or perfect gas. So the first property of the ideal gas is that the gas consists of large number of particles called molecules. So these large number of particles we call it as a molecules of the gas, and these molecules of the gas obeys the gas laws, and these gas laws are Boyle's law, gas law and gas laws, pressure laws at each temperature and pressure. So at each temperature and pressure these gas laws should be obeyed by the ideal gas. Then size of the molecule of the gas is negligible as compared to the volume of the gas. So volume of the gas is nothing but the volume of the container, and the size of the molecule of the gas is the spherical. The molecule of the ideal gas are in the spherical in shape, and therefore as compared to the volume of the gas, the size of the molecule of the gas is the very small, and therefore we will neglect the size of the molecule of the gas as compared to the volume of the entire volume of the gas. Then the fourth property of the ideal gas is that there is no force of attraction between the molecules of the gas. So whenever there are a large number of molecules, this large number of molecules will not attract each other or they will not repel each other. So there is no force of attraction between the molecule of the gas. Then the last property of the ideal gas is that the molecule of the gas obeys the Newton's laws of motion and they move in random direction. You know the Newton's laws of motion. There are the three Newton's laws of motion: Newton's first law of motion, Newton's second law of motion, and Newton's third law of motion. And all these uh, laws of motion are obeyed by the molecule of the gas. And I have already told you that the none of the molecule is in the rest state. They are not stationary. The molecule of the gas are not stationary. They are continuously moving from one place to the another place with all possible velocities. Then we will study the assumptions of the kinetic theory of gases. So these assumptions of the kinetic theory of gases are important from the examination point of view. Sometimes 2.5 marks question, or sometimes the 2 marks question may be asked on these assumptions of the kinetic theory of gases, and therefore it is the very important. So here I have shown here the one cube. It is the container of the gas, and a gas consists of large number of tiny particles, and these large number of tiny particles are called the molecules. In this slide I have shown in the box, in this box or in this cube, in this container, these pink spherical molecules are nothing but the gas molecules, and they are moving in random direction. They move in random direction, they move in all possible directions. They may collide with the wall of the container, they may collide with the other molecules of the gas. Okay. So the molecule of the gas, second assumption of the kinetic theory of gases is that the molecule of the gas are rigid and perfectly elastic spheres of very small diameter. So all the molecules are the rigid, they are like a cork ball, and uh, the collision between the molecules is the elastic, because in the elastic collision when the molecule collide with each other, then there is no loss of energy. So the third assumption of the kinetic theory of gases is that all the molecules of the same gas are identical in shape, size and mass. Then the fourth assumption of the kinetic theory of gases is that the actual volume occupied by the gas molecules is very small as compared to the total volume of the gas. So here there are a large number of molecules in this container, and if we add the volume of each molecule of the gas in the container, then that will be the volume of the actual volume occupied by the molecule of the gas, and volume of this container is the suppose capital V. So this actual volume occupied by the molecule of the gas is very small as compared to the total volume of the gas, total volume of the cube in which the gas molecules are present. Then another assumption of the kinetic theory of gases is that the molecule of the gas are in random motion. I have told you previously, because the molecule of the gas uh, are continuously moving. They move in random direction, they move in zigzag motion. So this zigzag motion is known as the Brownian motion. So that you have studied in the 12th. So the molecule of the gas are moving in all possible direction with all possible velocity, and they collide randomly with themselves and with the wall of the container. Suppose this one particular molecule is moving in this particular direction. So it will collide with the wall of the container, and its direction will be changed by the wall of the container. Or this molecule of the gas may collide with the other molecule of the gas, and when the one molecule collide with the another molecule of the gas, then its motion is changed, its direction is changed. Okay. So all the molecules are having the some velocities. This velocity ranges from very small value to the infinity value. So all the molecules are in motion. Another assumption of the kinetic theory of gas is that the molecule move with uniform velocity in a straight line in between the two collisions. The distance travelled in the between the two molecules in between the two successive collisions is called the free path of the molecule. So, when the two molecules collide with each other, in between these two molecules, the straight line path is there. So, the distance travelled in between the two successive collisions is called the free path. Then we will study the expression for the pressure exerted by the molecule of the gas. So, this expression for the pressure exerted by the molecule of the gas is not there is no derivation of this expression. Only we will take the use of this formula for the pressure exerted by the molecule of the gas that you have studied in the 12th. And with the help of this expression for the pressure exerted by the molecule of the gas, we will write that expression in the somewhat different forms, and from that we will draw the some conclusion, and that conclusions will be required for the further elaboration of the topic. So, for derivation of this expression for pressure exerted by the molecule of the gas, we will consider a given mass of ideal gas enclosed in a cubical vessel. Then the expression for the pressure P exerted by the molecule of the gas or on the wall of the vessel is given by P is equal to 1 by 3 mn upon V into C bar square. This is the equation number 1, where m is the mass of each molecule of the gas, n is the small n is the number of molecules of the gas, C bar square is the mean square velocity of the molecule of the gas, and capital V is the volume of the cubical vessel. So, from this expression 1, it is seen that the pressure exerted by the molecule of the gas is directly proportional to the mass of each molecule. From the expression 1, it is also seen that the pressure P exerted by the molecule of the gas is directly proportional to the N upon V. So, N is the number of molecules, N is the number of molecules of the gas, and V is the actual volume occupied by the gas. So, that will give us the density of the gas. N upon V gives us the density of the gas. Then from equation number 1, it is also clear that the pressure exerted by the molecule of the gas is directly proportional to the mean square speed. But we have seen previously that there are the n number of molecules in the cubical vessel, and mass of each molecule of the gas is the small m. So, m into n, it is equal to the capital N, and this capital M is the total mass of the gas. So, P is equal to 1 by 3 mn upon V into C bar square. So, we will write this expression in somewhat different manner. So, P is equal to 1 by 3, and instead of this mn, we will write here the m, and therefore, we get the expression as P is equal to 1 by 3 capital M upon V into C bar square. But M upon V, mass upon volume, is nothing but rho, that is the density of the gas, and therefore, we will write the expression 1 in somewhat different manner as P is equal to 1 by 3 rho into C bar square. So, this is the expression number 3. Then the same expression number 3 we can write in somewhat different manner as P is equal to 2 by 3 into 1 by 2 into rho into C bar square. And from this expression, 1 by 2 rho into c bar square is nothing but E. It is equal to kinetic energy per unit volume, and therefore we can write this expression in different form as P is equal to 2 by 3 into E, where P is the pressure exerted by the molecule of the gas with the wall of the container, and E is the kinetic energy per unit volume of the gas. So we have seen, this is the fourth equation. So we have seen the expression for the pressure exerted by the molecule of the gas in can be written in four different forms. So equation 1 is the first form, equation 2 is the second form, and equation 3 is the P is equal to 1 by 3 rho into C bar square is the third form, and the fourth form is the P is equal to 2 by 3 into E. So these are the four different forms of the expression for pressure exerted by the molecule of the gas. Then we will study the kinetic interpretation of the temperature. So let V be the volume of 1 mole of the ideal gas, T be the temperature of the ideal gas, small m be the mass of one molecule of the gas, and C bar square be the mean square velocity of the gas. And therefore, the number of molecules in 1 mole of ideal gas is the n, and this n is nothing but Avogadro number. So, in 1 mole of ideal gas, there are 6 into 10 raised to power 23 molecules are there in 1 mole of ideal gas. So, you can from this you can imagine the large number of molecules are present in the ideal gas. So, in 1 mole of ideal gas, how many molecules are present? So, there are 6 into 10 raised to power 23 molecules are present in 1 mole of a ideal gas. Then the expression for the pressure of 1 mole of a ideal gas, we have considered here 1 mole of a ideal gas, and then the expression for the pressure of 1 mole of ideal gas is given by P is equal to 1 by 3 m into n. Here n is nothing but capital N, that is nothing but number of molecules in 1 mole of ideal gas. So that is nothing but Avogadro number. So P is equal to 1 by 3 m into n upon V into C bar square. So PV is equal to, from this expression we can write PV is equal to 1 by 3 m into n into C bar square. This is our equation number 1. But ideal gas equation is PV is equal to RT for 1 mole of a ideal gas. If there are n number of molecules, then the ideal gas equation is PV is equal to nRT. Here we have considered the 1 mole of ideal gas, and therefore we have substituted here n is equal to 1. Then the ideal gas equation for 1 mole of ideal gas is PV is equal to RT. This is the equation number 2, where R is the universal gas constant and its value is 8.31 joule per mole Kelvin. From the equation 1 and 2, we get the left hand side of these both equations are the same, therefore right hand side must be equal, and therefore we can write it as 1 by 3 m into n into C bar square, it is equal to RT. So we will write this expression in somewhat different manner as 1 by 2 into m into C bar square, it is equal to 3 by 2 R by n into T. And here instead of this R by n, we will substitute the another constant, that is the K, and this K is nothing but Boltzmann's constant. So therefore we can write the same expression in different form as 1 by 2 m c bar square, it is equal to 3 by 2 into kT, where R by N is nothing but K, which is the Boltzmann constant, and value of this Boltzmann constant is 1.38 into 10 raised to power 23. 10 raised to power minus 23 joule per Kelvin. Okay. Then from this expression we can write it as 1 by 2 m into c bar square is directly proportional to the absolute temperature of the gas. And from this expression we can conclude that this left hand side of this equation is nothing but the average kinetic energy of the molecule of the ideal gas, and right hand side is nothing but the temperature of the absolute temperature of the gas, and there is a direct relation between the average kinetic energy of the molecule of the gas and the absolute temperature. And therefore from this expression we can conclude that the average kinetic energy of a molecule of ideal gas is directly proportional to the absolute temperature, and this is nothing but the kinetic interpretation of the temperature. Kinetic interpretation, why it is called the kinetic interpretation? Because kinetic energy, average kinetic energy is directly proportional to the temperature, and therefore average kinetic energy of the molecule of the ideal gas is a measure of the temperature. Higher is the temperature, higher is the average kinetic energy of the molecule of the gas, or vice versa. If suppose higher is the average kinetic energy of the molecule of the gas, then there will be the higher temperature of the gas, and therefore we can say that the average kinetic energy of the molecule of the ideal gas is a measure of the temperature. So higher is the temperature, higher is the average kinetic energy, and vice versa. Now we will see the typical case. So if temperature of the gas is 0, what is happening? If the temperature of the gas is 0, then the 1 by 2 m into c bar square is equal to 0. Average kinetic energy of the molecule of the gas is 0. And if the average kinetic energy of the molecule of the gas is 0, then c bar square is equal to 0. And this is happening only when the temperature is 0. So average velocity of the molecule of the gas, mean square velocity of the molecule of the gas is 0. Therefore, the velocity of the molecule of the gas is 0. So what is the absolute temperature? This temperature T is equal to 0 means it is the absolute 0 temperature. So from this we can define the absolute 0 of the temperature. So thus at absolute 0 temperature, the average kinetic energy of the molecule of the ideal gas is 0. Thus the absolute temperature is the temperature at which velocities of the molecule of the gas are reduced to 0. We have seen previously one of the assumption of the molecule of the gas, kinetic theory of the gases, that molecules are not having the 0 velocity. Molecules are continuously moving with different velocities in different direction. And if suppose the if suppose there is a temperature, absolute 0 temperature, then at that particular temperature all the velocity of the molecule of the gas are reduced to the 0, and therefore in this manner we can define the absolute temperature. So absolute temperature is the temperature at which velocity of the molecule of the gas are reduced to 0. Thank you. Now you may unmute yourself. हाँ, आप लोगों को समझ में आया? हेलो,
यस सर।
हाँ समझ में आया? स्लाइड अच्छे से दिख रही थी?
यस सर।
और